Okay, so in the last video we reached this point where we have an expression that involves the fugacity and involves measuring volume, temperature, pressure data, things that we can measure and figure out for gases. And so let's go ahead and rearrange this equation a little bit to make it a little bit simpler. First we'll divide by RT on both sides. So that'll get us just log P over F. Integral from, and we'll just call this 0. We've substituted just 0 instead of P approaches 0. We'll just say let's do this all the way down to P equals 0. So we can sort of think about this like integrating the absolute entropies where we start from 0, except for there's not a special part at the low pressure range or whatever. So anyway, that gives us the RT cancels, so we get 1 over P prime minus V bar over RT dP prime. Okay, and then often we express fugacities. We look at F over P, and we call this gamma, which is the fugacity coefficient. Okay, so we'd like to swap. We'd like to flip this entire equation. So let's go ahead and write this log F over P. So then everything in our fractions on the other side just gets reversed. Not that the fractions get reversed, but we've take the negative of everything, right? Because when we swap the top and bottom in the natural log, that's the same as taking the negative of it. So this becomes V bar over RT minus 1 over P prime dP prime. And then the final thing we can do is we can rewrite this in terms of Z. This is the compressibility factor. Just as a reminder, Z is equal to P V bar over RT. We saw this back when we were talking about real gases, all the way back in like chapter 16. And so if we can rewrite this equation in terms of Z instead. And so that gives us integral from 0 to P. If we make that substitution, then we end up with Z over 1, or Z minus 1 divided by P prime, dP prime. And we can say this is log of gamma now instead of log of F over P. It is log of F over P. We're just using this term of the fugacity coefficient. All right, and this is sort of the final form that we have. This is a way for us to calculate gamma if we can measure the compressibility factor as a function of pressure. And so that gives us a very clear way to do this. We can use any of the other expressions we have here too. This is just gives us a very clear, like if you measure compressibility factor as a function of pressure, you can then have fit that data to an equation, integrate it, and then you can find fugacity coefficients. And so that's the process that's used to do this. So just real quick before we look at some data on this, I just want to emphasize this fugacity coefficient. What's useful about it is it tells us how far our behavior is from ideal behavior. So if we have gamma equals 1, that tells us that we have ideal behavior, because then pressure and fugacity behave exactly the same way. And so gamma values of greater than 1 or less than 1 indicate non-ideal behavior. And that means that the fugacity and pressure are not going to be the same. This is similar to what we saw. The compressibility factor behaves similarly, right? And we can see in this expression, if the compressibility factor is equal to 1, in this integral, if Z equals 1, then this whole integral just goes to 0, and log of gamma being 0 means that gamma is equal to 1. So if the compressibility factor is equal to 1, we get ideal behavior. Basically sort of reiterating something we've said previously when we're looking at real gases. And so the fugacity coefficient, and we'll see a similar thing called the activity coefficient when we talk about activities, is a way of measuring non-ideal behavior similar to the compressibility factor. They're related to each other, as we see in this expression here. Okay, so let's go ahead and look at some data here. So these are figures from your textbook. This is looking at carbon monoxide, and what this is a plot of that function that we need to integrate. So coming back up here, right, so this function Z minus 1 over P. That's what's being plotted on the y-axis here. Now it's multiplied by 1,000 just so that it's in right? So that you don't have a bunch of 10 to the minus 3s on this. But this is how we calculate fugacity coefficients. So say you wanted to know the fugacity as the fugacity of, or in this case it would be log of the fugacity. Say you needed to know it at 400 bar. So what we need to do is find what is the area under this curve. And that would be equal to, that area, which is this integral, is equal to log of our fugacity coefficient. Now you'd have to scale it because this is 1,000 times it. So you'd have to divide by 1,000 before you calculate this. But if you were to use this exact plot. And so using that process, we can go from this plot, from that data about the how does z vary with p, to what's on the right, which is the fugacity coefficient as a function of pressure. And so we can see this behaves a little bit like the compressibility factor, right? It decreases below 1 at lower pressures, and then as the pressure keeps increasing, it increases above 1. For the same reasons as we saw with the compressibility factor, right? This has to do with the intermolecular forces, and which are more important, the attractive forces, that's this part, or the repulsive forces, that's this part, right, where it goes above 1. But this gives us a way to quantitatively get fugacity coefficients, which means we can find fugacities, and then we can use those in our thermodynamic expressions. Particularly relevant when we're talking about gas phase reactions and the equilibria involved in those gas phase reactions. To get accurate equilibrium constants, you need to use fugacities instead of pressures, because it's the fugacity that's related to the Gibbs energy, not directly the pressure.